Hi everyone, this is Lesson 6, Video 1, Work and Efficiency. The purpose of this video is to get us to be able to name and describe the laws of thermodynamics up to a point where we can describe them at a qualitative level and give examples of how they are at play in the world around us. By the end of Lesson 6, it is hoped that you'll be able to state and describe the four-ish laws of thermodynamics. It is hoped that you'll be able to explain thermal phenomena qualitatively using the laws of thermodynamics along with the kinetic theory of matter. It is hoped that you will be able to relate the terms heat, work, and changing internal energy for a system. And it is hoped that by the end of Lesson 6, although not in this video, you'll be able to calculate the efficiency of a thermodynamic process. First of all, let's start off with the Zeroth Law of Thermodynamics. This is a weird name for a law. Why would you have the Zeroth Law? This law was thought too obvious to be worth a mention when people were discussing the laws of thermodynamics. And yet after the three laws of thermodynamics had come into acceptance, it was felt that this law really did need to be said. And so they decided to include it as the Zeroth Law because it's foundational to the other three. This law relates to the thermodynamic equilibrium between materials. Consider three bodies, A, B, and C. Let's look at this law. Three bodies, A, B, and C. If body A exists, it has a thermodynamic state. It's got internal energy equal to the sum of its kinetic energy of its particles and the sum of the potential energy of its particles. Looking at these three bodies, if A is in thermal equilibrium with B, what that means is when you bring them together, energy will flow from one to the other equally. So there's no net flow of energy between them, no net flow of heat between them. So if that is true, and if B is also at the same time in thermal equilibrium with body C, then the Zeroth Law of Thermodynamics tells us that body A must also be in thermal equilibrium with body C, even though we might not actually observe it. So if we observe that A is in equilibrium with B, and if we observe that B is in equilibrium with C, then we can say, or we can predict, according to the Zeroth Law of Thermodynamics, that A must be in equilibrium with C as well. Okay, it's probably worth mentioning, what is thermal equilibrium anyway? We have an intuitive understanding of the fact that heat will flow out of hot substances and into colder substances. So that will continue happening. The hot substance will cool down, the cold substance will warm up, and it'll keep going until they're at the same temperature. And we have this intuitive understanding that that must be the point in which we have thermal equilibrium. That's pretty much enough for us in year 11. It looks at the idea that the average kinetic energy of the particles in A must be the same as the average kinetic energy of the particles in B, which must be the same as the average kinetic energy of the particles in C, if they're all in thermal equilibrium. This is our first law of thermodynamics. It's also one of the early laws that you covered in your science learning here at our college. Energy is conserved. That's something we tell year 8 every single year, and you would have heard it in year 8 as well. What does that mean, energy is conserved? We tell you in year 8 that energy cannot be created or destroyed. It can only be transferred from object to object, and it can be transferred from place to place, and it can be transformed from type to type. So that's how we cover it in year 8. What do we say in year 11? Okay, well, in year 11, the syllabus tells us this. A system with thermal energy has the capacity to do mechanical work. When the work is done, the internal energy of the system changes. Okay, so a system with thermal energy can do work. It can create a force. All right, fair enough. If you heat a balloon on the lab bench, it will increase in size. It'll push outwards. Fair enough. So, the hot air inside the balloon pushes against the elastic of the balloon, and that hot air system does work on the elastic of the balloon. Fair enough. Okay. What else do we see there? Because energy is conserved, the change in internal energy of a system is equal to the energy added by heating or removed by cooling plus the work done on or by the system. In year 10, we talked about work as being push versus distance. So we talked about work equals force multiplied by displacement. So here we're linking the internal energy of the particles to a force over a displacement. We're saying that due to the average kinetic energy of the particles in the system, they can do work on the surroundings and push outwards on the surroundings. Right. In year 11, we only need to understand this to a qualitative level. We just need to be able to describe it and give examples. But before we go any further, we have to ask the question, what is a system? What is an object? What is a system? Let's look at that. In short, a system is any group of things that we are studying. Any group of things that we are studying. They might be the gas particles in a box. We classify systems into three parts or three types: isolated, closed, and open. An isolated system is a system where no material can get in or out of the system, so the particles can't leave, you can't get new ones in, you can't get old ones out, and no energy can be added into or out of the system. The universe is the only real isolated system. If you wanted to imitate an isolated system in the laboratory context, you might imitate one. For example, you might get a really good esky with an airtight seal and put a whole ton of ice and drinks into that esky. Well, the ice and the drinks in the esky, that's the system. And when the esky's closed, none of the ice or drinks can get out. No new stuff can get in. And because it's an esky, a really top-notch, high-quality esky, no heat can get into the system, no heat can get out of the system. That would be a simulation of an isolated system. In a closed system, no materials can get into or out of the system, and yet energy can flow into and out of the system. That's a closed system. So the planet Earth is kind of like a closed system because, you might think in broad sweeping terms that nothing gets into the Earth from outside, deep space, nothing gets out of the Earth from the Earth out into deep space, but we do receive heat, or we do receive light from the sun coming into us, and we do emit our own radiant heat outwards into the universe. So the Earth is kind of like a closed system, if you ignore the fact that we're sending rockets up into space, which is basically leaving the Earth, and we're also receiving meteorites down onto the Earth, which, these two things, they're proof that it's not really a closed system, but we'll just ignore that for this example. An open system. An open system is any system you're studying where new material can enter in, material from the system can get out, but also at the same time, energy can come in and energy can come out. So as I'm sitting here looking at my garden out through the window, I've got my pond. I've got a neat little pond there. There's all sorts of plants around the outside of it. Insects are coming in and out all the time. Birds are coming in and out all the time of my little pond garden. So materials can come in and out of that system anytime at once. And energy can flow in and out of my pond garden system anytime at once. From the sun, electricity comes in from outside to move the pump, which causes the pond water to circulate around the various little ponds that I've got, little basins that I've got. So my pond garden, looking out through my window here, that is an example of an open system. Energy comes in and out, matter comes in and out. So there are three different types of systems. Now that we understand that, returning to the first law of thermodynamics, a system with thermal energy has the capacity to do mechanical work. Let's think about that. Okay. If you could imagine a plugged plastic syringe, get yourself a rubber stopper, basically put it over the edge of the syringe so no air gets in, no air gets out. All you've got is a plastic tube with a piston, and the piston is pretty much airtight. If you put that piston under a tremendous amount of pressure, then you have yourself a system inside of the cylinder of the syringe. That system is made up of gas particles, and they're bouncing around at great velocity off the sides of the walls and off the plunger of the piston as well, bouncing around. If you remove the force of your hand from the plunger of the piston, you are going to see that the gas inside that syringe is going to push the piston, push the piston out of the syringe. That's an example of a system doing work on an object, pushing against the plunger of the syringe. When a system does work on an object, that's energy that's being produced right there. That's energy that's being used. Where the energy come from? It came from the internal energy of the system. It came from the kinetic energy of the particles striking at the walls of the cylinder and the walls of the piston and pushing it outwards. So as that piston is pushed out, the internal energy of the system of the gas inside the cylinder goes down. If you have a conical flask with a balloon over the top of it and you place it into a bath of hot water, we're going to see that heat is going to flow across the glass boundary into the gas inside the conical cylinder. Now that means that the internal energy of the gas inside the conical cylinder is going to get quite high, and it's going to have the ability to do work. What's the work that we're going to see? We're going to see the work done by that system inside the conical flask is going to push outwards on the glass of the conical flask, which is not going to do anything at all, but then it's also going to push outwards onto the elasticized balloon, which is going to first of all stand up and then start to inflate. This is another example of a system, a thermodynamic process in which a system does work on something. And as it pushes outwards onto the balloon, causing it to inflate and expand, the work done there, that energy has come from inside the internal energy of the system. And so the internal energy must decrease as the balloon expands outwards and increases. As work is done by the system, internal energy reduces. There is a mathematical equation to describe this situation. Delta U equals Q plus W. We remember that U is the symbol we give, capital U is the symbol that we give to the internal energy of a system, the sum of its kinetic energies and the sum of its potential energies of all its particles within itself. Delta U does not mean the same as capital U. Delta U means the change in the internal energy of the system. So if you allow a system to receive heat, so if you have a glass box with a gas inside and you put a heat lamp onto the glass box, then the particles inside the glass box are going to receive heat. And so the internal energy will increase. There'll be a delta U that's positive. If you take your glass box and drop it into the snow outside, we don't have snow outside, but if you drop it into the snow outside, then heat is going to flow out of the system. That would be negative delta U. If you have a system which has a lot of internal energy and you allow it then to do work by pushing out a piston, the system does work, internal energy goes down. If you push the piston back in, then work's done on the system. And so delta U increases. So delta U equals Q plus W, where Q can be positive if it's heat going into the system, negative if it's heat coming out of the system. And W, work, can be positive if it's work done on the system, and negative if work is done by the system. Again, it's good to have the equation there to help us see what's going on. However, we only have to describe what's going on with the first law of thermodynamics. We have to give examples and describe. That's all we're required to do in year 11. Again, turning to the idea of systems, we remind ourselves that the system is the thing that we are studying. In this graphic that we see here, the system is the gas inside of a cylinder. This is worth mentioning because this is a classic diagram that we use all the time through physics. And if you study physics at university, you'll see this diagram time and time and time again. As you start to deal with this stuff mathematically, they'll use this diagram to introduce the math of this part of the course. We don't have to do that in year 11. Now, the system is the gas. The glass cylinder that the gas is inside is rigid. It's strong. It can't move. It can't be forced. The piston is airtight. Gas can't escape and it can't get in. The piston is frictionless. It's sitting on top of the gas in the same way that a toy boat sits on top of the pond. It's sitting there. It's being held up by the gas. As the gas particles go zipping around, bouncing off the walls, the floor, bouncing off the piston, every time they hit the piston, they are they are rebounding off the piston, causing a bit of force. Now think that there's not just 10 or 20 particles there, there's hundreds and thousands and millions of particles, and they're all hitting the piston, pushing it upwards, and providing a force that opposes gravity pulling the piston down. Okay. And it'll sit there and it'll stay there forever, and that's fine and good. Now, if we were to increase the internal energy of that system, then naturally the particles will be zipping around a lot faster. If they're zipping around a lot faster, they're going to hit the walls, they're going to hit the floor, they're going to hit the piston a lot harder, which means that they're going to hit the piston, and when you sum them all up, the forces being applied to the piston is going to be greater than the force of gravity. What are we going to see happen? The piston is going to be moved upwards. This is work being done. So if we add energy to this system, for example, turning on a Bunsen burner, we will see that the system will then release energy in the form of work, pushing the piston upwards. The second law of thermodynamics. All energy transformations involve some heat loss. Now, in lesson 6, we will talk about efficiency. This is where efficiency comes into play. No matter what you do, all energy transformations involve some heat loss. You turn on a light, electric energy becomes light energy. Well, guess what? It's not just light energy, there's always heat loss. If you turn on the engine of your car, then chemical potential energy in the fuel becomes kinetic energy of the car. Well, guess what? The engine gets hot, there's heat loss. This is the second law of thermodynamics in play. There is no such thing as a perfectly efficient machine or engine. Doesn't exist. That's what the second law tells us. All spontaneous change occurs in the direction of increased entropy. Now, those first 2 points, they're quite intuitive. We live our whole lives, we see it all the time. This third point takes a bit of thinking. Spontaneous change, anything that happens naturally, will always happen in such a way as to increase entropy, randomness. We haven't really covered entropy yet. Entropy is a representation of how chaotic a system might be, how random a system might be. If you throw marbles into a bucket, they will spread around the bucket pretty much evenly. They won't all clump on one side for no reason unless the bucket's at a tilt. All spontaneous change occurs in the direction of increased entropy. If you have a glass box full of a gas, at any given time, the gas particles will be spread evenly throughout the glass box. They won't just be clumping up in the top left corner of the box. That would be an ordered system. The natural state of things is chaos, is randomness. And all spontaneous change will always result in randomness, in an increase in randomness, an increase in entropy. Finally, the second law tells us that heat will always flow from high temperatures to low temperatures. Now, we know that intuitively, but here it is telling us as a part of the law that if you bring a hot object and touch it to a cold object, the heat does never ever flow from the cold object to the hot object. That is a law. It doesn't do that. It must flow from the hot object to the cooler object. So in short, the second law of thermodynamics tells us that chaos will reign. Chaos is king. The second law of thermodynamics. Dialing it back a bit to the second point on efficiency, we have an equation for efficiency that we've been using a fair bit in our lives. It's just another example of the percent equation. We define efficiency as the useful energy transformation as we, the human, sees it, divided by the total energy supplied, multiplied by 100. That is our efficiency equation. In symbols, we say eta, that weird looking N shape there to the left of the equation with the long nose is ETA, eta. So eta, efficiency, is equal to the energy out that we see, the human sees as useful, divided by the total energy in, multiplied by 100. So it's the light energy coming out of the globe, divided by the electrical energy going into the globe, multiplied by 100. That's our efficiency of the globe. And for an LED globe, that'll be something like 95%. For a fluorescent globe, that'll be something like 20 to 40%, depending on the model. This is efficiency. The third law of thermodynamics. It is impossible to achieve absolute zero. Now, in our previous studies, we talked about temperature and scales, and we learnt about the degrees Celsius, the Celsius scale, and we learnt about the Kelvin scale. And the thing that we said was different between them is that the Kelvin scale is an absolute scale. The temperature scale, the Kelvin scale, is representative of the average kinetic energies of the particles. So in theory, there would be a point where the average kinetic energy of particles can vary, go up and go down, depending on if something's getting hotter or getting colder. It can go down and down and down and down and down. But whilst we can conceptualize the idea where the particles in a system might have average kinetic energy equal to 0, the marbles in your box are not moving, according to the third law of thermodynamics, it's impossible to actually achieve 0 Kelvin. We might express it in words like this. It's impossible for any process, no matter how idealized, to reduce the entropy of a system to its absolute 0 value in a finite number of operations. Well, what does that mean? Here's the example. I've got a cold object. I want the cold object to reduce in temperature. I want the cold object to be 0 Kelvin. It's not 0 Kelvin right now. I want it to be 0 Kelvin. What do I do? Okay, well, I just leave it on the bench and let it cool down. But what if the surrounding temperature is already the same temperature as the cold object, which it probably would be anyway because it's been sitting there for a while. So how do I make it colder still? This is what I do. I bring in a colder object. Now, according to the second law of thermodynamics, heat will flow from the cold object to the colder object. This will continue until the colder object is the same temperature as the colder object. Can you see my meaning there? This will continue until the two objects are the same temperature. One of them, the one that we had to start with, will be colder and the other one will be not as cold as it was, but doesn't matter. Our object, the one we wanted, is colder. Okay, remove our little assistant. I still haven't got this colder object at 0 Kelvin. What do? I bring in another colder object. This object is even colder. Well, what's going to happen? We are going to see that heat will flow from the colder object to the even colder object. Until what? Until our original object is colder again. Then we remove our second little helper. So we continue doing that process. If we get close to 0 Kelvin, each time we bring in a colder object to drag heat away, the new temperature of our object is going to be somewhere between its starting temperature and the temperature of the colder object. They'll meet an equilibrium between the two of them. So even if that magical new object we drag in, that we bring in to take heat from our object, even if that object is already at 0 Kelvin, the end point, equilibrium point of temperature for our object and that object together is above 0 Kelvin. The only way to get our object to 0 Kelvin is if the magical object coming in from the side that is brought into thermal contact with it is at negative to 0 Kelvin, which by definition is impossible because Kelvin is an absolute scale. So that's the end of the video. Where to from here? Take a moment to jot down ideas from this video into your physics notebook. Try to do it from memory before you go back and get specifics. Read and take notes on Chapter 2.1 of the Pearson text. Complete Chapter 2.1 Work and Efficiency questions from the Physics Pearson text. And when you're ready, watch Lesson 6, Video 2, Work and Efficiency for examples of efficiency. I hope that was useful.